Okay, so let's wait for a couple of more minutes to see if anyone joins, then we will start. So Tanish and Aksha, so have you guys joined the previous session from 3 to 5?
Yes, sir.
Okay, fine.
No, sir. I haven't joined the previous session last Sunday.
No, this session today previous session 3 to 5 of Mr. Atib.
No, sir. I was out somewhere.
Okay. So how are you doing in your assignments in the course?
This week I got just pass
This week you just got?
40.
Okay. So this week was with P-N Junction?
Of course, sir.
Okay. Okay.
I was
S-
unable to solve the problems with um,
Okay.
sinusoidal wave diagrams they have given. No,
Okay.
I was unable
So
to solve
just
this.
try to see where in the questions I am discussing where you can chip in your questions or your doubts. Okay. So I would say that just don't solving the assignments won't be sufficient. You need to also cross check with the solutions, right? Where you are going wrong and where you are going, because you see the concepts are same. Where you may go wrong is that you may not be able to visualize the problem properly. Formulas and all those calculation mistakes is understandable, right? But is it something from the calculation mistake point of view or from the conceptual end?
Conceptual end.
Conceptual end, right? Okay.
Yes,
Okay.
sir.
Sir,
Okay. Yeah.
lectures are in depth, very much, very depth now. So, sir, it takes time to follow up in the assignment every week. So that's why it gets.
So what I can suggest you that that the lectures and the problem statements are posted simultaneously. Okay. So you get how many times? 10 days of time or 7 days to submit the assignment?
7 days.
7 days, right? So one thing you can do, you can devote at least. So are you guys making notes from the lectures?
Yes, sir.
Okay.
Yes, sir.
So do make your own notes. Okay, that helps. Do make your own notes and try to solve some problems, example problems before you're solving the assignments. Okay, For example, you have seen about the Donald E. Nieman book, right? And also SMG book. So try to solve some of the problems which are given in their examples, and if time permits, some of the problems from the exercise. So then I think it will be helpful or easier for you, because I know that Donald E. Nieman has uh, some numerous example problems. SMG may not have that many problems, but these two books should be sufficient for you to follow up this course. There are
Okay.
some advanced books, but I don't recommend them at this stage. Okay. And also try to discuss among in your college professors also. If you are stuck with some problem, you can discuss with them also, right? They are always welcome.
Yes, sir.
So the motto is to invest yourself some more time. Okay. So give some more time. I think it will be good. And also, whatever you have been reading, you might have forgotten about the quantum mechanics part and all. Try to revise your notes, own notes, whatever you are making, right? That will help you in the end semester.
Yes, sir.
Yes, sir.
Okay. Okay. So let's start today. Just give me a minute. So if you have followed the 3 to 5 session, most of the problems will be similar. So I hope that whoever has followed would be able to answer some of my questions. This way I will get to know that whether they have understood the concepts or I need to elaborate something more. Okay. So, okay, welcome everyone. This is NOC EE-91 NPTEL tutorial on semiconductor devices and circuits. This course is offered by Professor Sanjeev Sambandan, and I am Debashish Nandi from IIT Kanpur. I am a PMRF scholar assigned as a TA to this course. So we go live every week 5 to 7. So this is the 7th week. Okay, these are some of the prerequisites. You must be familiar with them. This is for those people who are joining live, and also I would suggest that at least a thorough understanding of the, or at least thorough revision of the course material, and one attempt of the assignment problem should be helpful in following up with the content of this tutorial. So this is week 7. So let's begin. So, okay, this is a circuit diagram has been given, right? So what it is given? It is given that you have some DC voltage, you have some small signal AC voltage, and a diode is connected with a resistor in series. Okay. So can any of you tell me what is the purpose of DC voltage and what is the purpose of AC voltage? Why do we do that? What is your understanding? I just want to know. Anyone?
DC voltage doesn't fluctuate. AC current, on the other hand, it is a direct current. Like it doesn't fluctuate. AC current fluctuates.
Right. That is very true. But what is the purpose of connecting any device, or more precisely say nonlinear device, for in with some DC voltage? We call it bias, right? Have you heard of this term, bias?
Forward bias, reverse bias.
Yeah, bias means it is tending to something, right? You must have heard this term in your probability course, that if coin is unbiased, that means it doesn't tend to something or some output. Okay. So the purpose of DC voltage is to bias the device. Okay. So why do we need to bias the device? See, if you have some, let's say, IV characteristics of this kind. Okay. This is your diode IV characteristics in the forward bias. So you see, at each point, the trend is changing, right? It is not linear per se. That means, suppose you want to fix your diode at around this point. That means, say this would be your then VDC, let's say, okay? and this point will be your VIDC. So what happens is that suppose you are taking a curve like this, okay, and you are fixating a point called DC bias point, operating point, or the quiescent point. Okay, this is called bias or quiescent point. Okay, so what happens that you are fixing your voltage or the diode operation at this place, and now on top of that you are applying a sinusoidal voltage. So what will happen? This sinusoidal voltage, this is your voltage axis. Okay, so this sinusoidal voltage will act how like this, it will act like this. So so what happens if you draw two lines, so your sinusoidal voltage will get limited on that, so your point will get shift between these 2 points, right, A and B. Let's call it U Q. So your point will move from A to B. Okay, and the beauty is that in this region you can assume these characteristics to be of a straight line. Okay, this is your A, this is your B, and this is say Q. So at this small region this becomes linear. Okay, and we are very much we know we can use linear calculations very smoothly because we are very much comfortable with the straight lines and all. Okay, so the main purpose of the DC voltage is to fixating this Q point or this bias point, and then apply a small voltage so that around that small point or around that Q point we can assume the characteristics to be linear. Okay, and why does linear is of requirement, that you will learn in the BJT or in a MOSFET part where we will discuss about the amplifiers. Okay, for this portion you just know this much, that for converting the nonlinear characteristics to a small signal or linear approximation, we do have to bias the point in this region. Now suppose you are same point, you are this Q point, you are shifting at this place. Okay, then you see you cannot use the small signal approximation, right, because this part is not linear. This part or this part beyond something, this you can consider as linear. Okay, for a small voltage, this you cannot consider as linear. Or to consider it linear, what you will need to do, you will need to take a very narrow region. That means your this sinusoidal signal or this 5 millivolt needs to be much lower. Okay, then only in that region you can be able to approximate this characteristics as a linear characteristics. So this is the purpose why you just okay. So this is the purpose why you connect your circuit like this. Okay. So now it is mentioned that your diode is in forward bias. Okay. So that is evident also. So this is your positive terminal connected to positive, and this is your negative terminal connecting to negative of the diode, right? And DC current is this. Okay. So in small signal sense, when you have a linear or a small signal approximation of the circuit or linear approximation of the circuit, you must have heard about, if you have gone through the lectures, you must have heard about that you can approximate your diode with a resistance in parallel to a capacitance. Are you agreeing with me? This you can write approximately same. Is that okay?
Yes, sir.
Sir.
Why is it okay? My question is, there is inductors also. There are inductors also. So I may come up with any circuit, resistance, capacitance, and inductance. So why I am doing a resistance in parallel with a capacitance? Any comment on that? you see, in a wire, whenever there is some current flow, right, there has to be some resistance in the wire, or for that matter of any component. Okay, if there is a current flow, there has to be some potential drop across the current flow, so there will be resistance. But you are telling that there is capacitance also. Do you know the origin of this capacitance, where this capacitance is coming from, and how people actually knew that it is a resistance in parallel with capacitance? See, the way they go about is that they made a circuit like this. Okay, so this is a small signal. This is some DC voltage. So this is, let's say, small signal is Vm sin omega t, and they were measuring this current. Okay, current, let's say Im sin omega t plus some phase. Generally, it will add up some phase. Okay, if it is DC, then the phase will be simply zero. So if no reactance in the circuit, then your phi will be zero. Now, when they have measured the diode in this way, so they have tracked down phi, how phi behaves. Okay, how phi behaves. Is it phi greater than zero or phi less than zero? How is it? So, can you comment if phi is 90-degree? What is the, how can I, what will be my diode equivalent circuit? You see, you have a which is current which is leading voltage by a phase phi. Fine. So if phi is 90-degree, that means your current is leading the voltage 90-degree. What kind of component it should be? When a current leads the voltage of 90-degree by 90-degree? Anyone? This is from +2 physics, right?
Inductor.
No, no, it should be capacitor, right? See, they again, how will you remember that? You are remembering it, right? Don't remember, just for suppose if it is a capacitor, okay? Let me just draw two things. A voltage is there, some current is flowing, okay? A voltage is there, some current is flowing. So if I use Laplace domain, will that be okay with you? Will you be able to understand?
Yes, sir.
Okay. So if I say I of S, so what is I of S for this case? If it is C, then it will be V of S over X of S, XC of S. That will be V of S over 1 over SC. That will be SC in times V of S. So this S is nothing but your J omega. This introduce a phase of, or if I say I of S, it will be angle V of S plus 90-degree. This S will correspond to 190-degree positive shift. Similarly, if in this case, if you put this, it will be V of S over XL of S. That will be V of S over your J omega L, or in Laplace it would be S of L, right? If it is S of L, then what is the phase? If you write it in I of omega, it will be V of omega over J omega L, or minus J of V of omega over omega L. This minus J will create a phase shift of minus 90-degree. So if your current is leading the voltage by plus 90-degree, so you can say that is a capacitive component, okay? And other way it is an inductive component. Is that okay?
Sir.
So from now on, if anyone asks you this question that whether current should be leading the voltage or not, you just simply do the Laplace thing and you see the whether you are getting plus j omega sometimes something or minus j omega times something. Okay. So from that you will be easily getting that whether it is plus 90 degree or minus 90 degree. Fine. So there is nothing to remember. So what we are discussing, that when people are studying this phi, so they saw that phi is greater than 0. That means that I have some capacitive component in the equivalent circuit of the diode. Okay. So now you are this much sure that this diode will be in small signal equivalence. In small signal equivalence, this will be nothing but your a resistance. Because why resistance? Because at DC there will be some current, right? What do I mean? That if it is, let's say, RD and it is CJ, then if there is some, if suppose your omega is equal to 0, right? That means your DC, right? This means DC. DC is which point? These points. These points are DC, right? Wherever your sinusoidal signals are crossing 0. So it has to satisfy that condition also. So if omega is equal to 0, what is your 1 over j omega c? It is infinity. That means you have an open circuit. So your equivalent circuit will become just a resistance and your capacitance gets open circuited, right? So some current has to flow. That means it has to have some resistance. Okay. So now what we will do, we will consider two conditions. Yeah, you have any question?
Yes, sir.
Yeah.
So you said omega is equal to 0. After that, I don't follow. What?
Okay. So what is your X of C, or the impedance, equivalent impedance for a capacitor? It is 1 over j omega c. You are agreeing with that?
Yes, sir.
So if omega is equal to 0, so what is the impedance
Mm,
for a capacitor?
Infinitive.
It is
Infinite.
infinity. What does infinite impedance means?
The circuit is open circuit.
Circuit is open, right? So this part will be open at DC. Or in another way, you tell that you generally say that capacitor blocks DC, right? This is
Yes,
the
sir.
same thing. So that means you will only be living with only resistance. Only resistance will be there. And also you know that at DC there will be some non-zero current.
Yes, sir.
Okay.
Okay, sir.
So this is why there is a resistance and there is a capacitance in the equivalent small signal circuit. Now the question is how this scenario will change when I am into a forward bias or and I am into a reverse bias. So can you tell me what is the equivalent circuit of a capacitance of a diode in forward bias? This is your C depletion, this is your C diffusion, fine, and this is your RD. And what about reverse bias? It is just C depletion. Now tell me how many of you have gone through this part of the lecture?
I have, sir.
Okay, so tell me that why there is first thing is first let us deal with the resistances. Okay, first let us deal with the resistances or RD. So why there is no RD here?
Be-
Intuitively what happens if there is no RD? That means your RD has somehow gone to very high or infinity. That means I had to open circuit it. Okay, So who was telling that? Acha, can you please comment that why there will not be any RD?
Actually, in my lecture notes, I have drawn both capacitance and resistance in parallel to each other for
That
reverse
is
bias.
for reverse bias.
Yeah,
Okay, just let me tell you one thing.
I have written for step junction, C depletion is directly proportional to 1 by VA to the power 1 by 2. That's what I
No,
have
no, no,
written.
no. I am not telling about any formulas. Okay, if you will go to the formulas, you will be lost. Okay, first thing is intuition. Second thing is qualitative understanding. Third thing will be the quantitative understanding or the formulas. Okay,
Okay, sir.
so follow this step, then only you will be able to understand. Otherwise, it will be very difficult. You will be lost in the formulas. Okay, so see
Okay.
what is the diode current formula? ID is equal to Is times e to the power Vd over Vt minus 1 for an ideal diode.
Yes, sir.
So what will be the resistance, small signal resistance? Let me just differentiate it with this. So what I will get? Tell me what I will get? E to the power Vd over Vt. So what is your resistance? dVd over dId or your Rd, differential resistance or the AC resistance or the small signal resistance. What will it be? It will be your Vt over Is e to the power Vd over Vt, right? Now in forward bias, this quantity is much higher than this, right?
Sir.
Do you agree?
Yes, sir.
Why it is so? Because if your Vd becomes greater than 3Vt, so what is my room temperature 3Vt? It will be around 78 millivolt, right? But what is the cut-off voltage or cut-in voltage? It is around 700 millivolt, right? So obviously to make it in forward bias, you have to or have a significant amount of current, you have to have this approximation. So if your Vd becomes 3Vd, they greater than 3Vt in forward bias, so what happens? Your Id becomes Is into e to the power how much? That is greater than 3. Can you compute and tell me what is greater than 3 minus 1? What is e to the power 3? So your e to the power 3 is how much? 20, right? It is around 20. So this 20 minus 1 you take as 20, okay? That means this component becomes much more than this minus 1 at forward bias. Understood? So that's how you write it as Vt over Id in forward bias. Okay. So now what happens? Let me go to reverse bias case. What will be the formula of current in reverse bias? It will just remain same. Fine. But in this case, your Vd is negative. And if your Vd is less than minus 3Vt, then what happens? Then your e to the power minus 3 is much less than 1. So this quantity becomes what? Minus 1. So your Id becomes minus Is. That is why it is called reverse saturation current. Are you following?
Yes, sir.
So now if you compute the resistance, so dId by dVd will be how much? Can you unmute and tell me? From this to this, what will be did by dvd?
Minus is.
Did by dvd. It is simple differentiation, right?
Yes, sir.
You are differentiating a constant value. So what will you get?
0.
You will get 0, right?
Yes, sir.
So what is your dvd by did?
DVD by 0. No,
It will be infinity, right? If this is 0, then just 1 over 0 is infinity, right?
yes, sir.
So that means your R is becomes infinity. That means open circuit. Okay. So do you see why there will be no RD for reverse bias case?
Because RD becomes
Because
uh,
RD becomes very high,
very high.
right?
Okay, sir.
Understood?
Understood, sir.
Okay. So this is about the resistances. Now what about the capacitances? So I have drawn two capacitances here, depletion and diffusion. In another case, for reverse bias, I have drawn depletion. Okay. Depletion capacitance you are aware of.
Yes, sir.
What is that?
The
C
capacitance of the
depletion.
circuit in depletion mode.
No, sorry.
Uh, in depletion mode.
No. There is nothing called depletion mode, right? See, what happens is that if it is a PN junction, okay. Let's say this
Reverse
is
bias.
P, this is in. No, not reverse bias. This is your suppose something. This is called depletion region, XD. Same thing happens in case of metal semiconductor junction also in one side.
Yes, sir.
So that means you have some, this is immobile charges. So you can assume that it as a capacitive plates. If you apply some voltage across this, so it will be something positive, something negative, and this is just a parallel plate capacitor. Do you see?
Yes, sir.
If this is a parallel plate capacitor, what is the parallel plate capacitance of if this is D and area is A, say? So it will be epsilon A over D. This you know.
Yes, sir.
So for depletion capacitance, what it will be? It will be epsilon of silicon multiplied by the area over this depletion width. This is what we have been discussing since last three sessions.
Yes, sir.
For metal semiconductor junction, it happens only at the semiconductor region, but for PN junction, it happens in both sides.
Yes, sir.
So this
So,
is your depletion capacitance.
yeah.
So what is your XD by the way? You
Depletion.
remember your XD is your VBI minus B over Q 1 over NA plus 1 over ND, right?
Yes, sir.
These derivations and all we have discussed in case of metal semiconductor junction, and the professor has also posted the discussion for PN junction, right?
Yes, sir. In last class also you mentioned this.
Okay, so this is your depletion capacitance. Okay, so what does depletion capacitance see? Okay, just tell me this thing, among these three quantities, what changes with voltage? Epsilon s, A or XD, what quantity among these three, what is changing with voltage? XD is
D, sir.
changing, XD is changing with voltage, right?
Yes, sir.
So you see, in a PN junction, this is your this region will change. So let's say this is XD0 in case of equilibrium. XDF depletion width in forward bias, XDR depletion width in reverse bias, and XD0 depletion width in equilibrium. Okay. Now tell me, XDF will be greater than or less than XD0?
Greater.
XDF forward bias. If you are using forward bias, this term will reduce, this will reduce. So XDF will be less than XD0, right? Suppose you are using a forward bias, okay?
Yes, sir. For reverse bias, it will become plus. That's why XDF will be increasing for reverse bias. In forward bias,
So XDR will be greater than XD0.
yes, sir.
But in both cases, you see you have a significant amount of XD or the depletion width. So these capacitance or depletion capacitance present in both forward bias and reverse bias. Okay. Now the question comes, what about the diffusion capacitance? So can you tell me what is diffusion capacitance?
The response of minority charge carriers to applied voltage.
Good. So suppose this is your PN junction. Okay. Let's say this is your P side, this is N side. So it will be something like this. So how will be your minority carrier profile? Your minority carrier profile will be something exponential and it will be like this. You have seen this, right?
Yes, sir.
Let's say, let us take only. So what is the type of carrier? This is what type of carrier? Holes or electrons?
Or it. Hold,
What
sir.
type of carriers are this? These are holes, right?
Yes, sir.
So let's say this is Q of delta P. Okay. And let me just zoom this part. So you have something like this. This line is this line, okay? And you have this is X and this will decay like this. This is your Q delta P. So if I just draw a straight line at this point across its slope, what will this distance be? What is this distance? LP is known as diffusion length, right?
Yes, sir.
And if I consider that this is my entire charges or minority charges due to minority carriers, then what would be my QP for minority carriers? It would be Q times dP times LP into some area. Okay, this is the area of this rectangle and in the third direction we have some area. Okay, so this area would be, let's say this area is your A. So you have total charge. This are the dimensions. Okay, these dimensions are of centimeter cube. This is of centimeter minus 3. This dimension coulomb. This is also coulomb. Okay, this cancelled. So dimension wise also this is okay. Now if I need to find out the capacitance, what will I do? I will have to take the differentiation with respect to voltage. So my Q is constant, LP is constant, A is constant. I have this over del V. So what is my dP? You know this, this equation, you know. What is this? Anyone? Minority carriers of minority carrier concentration of holes in N side at equilibrium. Okay. So what happens is that if you take differentiation of this, you will get, this is called as C diffusion. So your C diffusion becomes how much? This will be Q LP times A times over VT times delta P, right? And if you use your further simplification, you will find out this to be ID times your tau P over Vt. This tau P is nothing but the, what is this tau P? This is called minority carrier relaxation time. Okay. If you have gone through the lectures, you will be able to understand these things. Okay. So ID have significant ID we can have in forward bias. This will be mainly present in forward bias. So what happens in reverse bias? Now let us start from this equation. Okay. In reverse bias, what happens? This delta P is equal to Pn0 e to the power V over Vt minus 1. So this term will be negative, much less than minus 1. So what I will have, delta P will be minus Pn0, right? Okay. So if you take your dQp over dV, it will come out to be 0 for reverse bias case. So C diffusion in reverse bias will be 0. What does that mean? 1 over j omega C diffusion is infinity. That means open circuit. Okay. That means if there is some C diffusion also, it will be just open circuited. So we will leave with only this C depletion, right, for reverse bias. So on a concluding remark, you can say that in your forward bias, you have your equivalent circuit like this. This is C depletion, C diffusion. This is R. Or you can simply club these two capacitance or write it as C forward, which is equal to the sum of this C depletion plus C diffusion, and you will have a resistance, okay, RD. And for your reverse bias, what you will have? You will have only C depletion. So is this okay with all of you? Why the
Yes, sir.
equivalent circuits behave like that?
Yes, sir.
Okay. So understand these concepts very carefully, or you may just remember this and go back to the concept also. That will also work for this course. These equivalent circuits you try to remember, okay? Or this part will also do. So now let's go back to the question. So in forward bias, what will happen? This equivalent circuit will be, you have some AC, you have some DC, you will have some resistance in parallel with capacitance, and you have some resistance in series, right? This will be your RD, this will be your, how much, what is that? CF, forward bias. CF is given as 1 nanofarad, omega is given as 10 to the power 6 radian per second, and your DC current is given. So what was your RD? Your RD was this, right? VT by ID. So RD would be 26 millivolt over ID was given 13 microampere. So that will be 2 kilo ohm. Okay. So now if you draw an equivalent circuit, so it will be something like this. You have resistance, you have a capacitance, and you have a resistance here. This is your 2000 ohms, this is your 100 ohms, this is your 1 nanofarad, this is your 5 sine omega t millivolt, and that is also omega is equal to 10 to the power 6 radian per second. Okay, so we want to find out what is the magnitude of I. So what we will do first? We will first compute the equivalent impedance. Okay, so how will you calculate the equivalent impedance? This is your 200 ohm, this is your 1 nanofarad. So this is your, okay, just let me, for the simplicity, I will draw like this. So there is some impedance, and here is some impedance. Okay, so this is your 100 ohms, this is your 2000 ohms, and this is how much in ohms? Can anyone tell me? This will be 1 over j omega c, right? That means minus j over omega c. That means minus j over, what is your omega? Omega is 10 to the power 6. This is 10 to the power minus 9. That means that is minus 1000 j. Okay. It is minus 1000 j ohms. Okay. So I want to find out this R in or Z in, I would say. So can you do that? Until this step, do you understand?
Yes, sir.
Okay, fine. So now this is a parallel contraption. So what will be if I do like this and then series? So this will be what? This will be, let's say this will be 2000 multiplied by minus 1000 j over 2000 minus 1000 j, parallel combination of two impedances, right? So that will be how much? Minus 2000 j over 2 minus j minus 2000 j. So if I do 2 plus j, and it is also multiply 2 plus j, and here also 2 plus j. So I will get 2 square plus 1, 5. That means minus 400 j, 2 plus j. That will be your plus 400 minus 800J. So this will be 400 minus 800J, and this is 100. So this will just add up the real component. So you will have a equivalent circuit like this, and here you have this your signals. So this is how much? Your 500 minus 800J. This is your 5 sine omega t millivolt. So what will be your I? So modulus of I would be modulus of V over mod 500 minus 800J. So this is 5 milliampere. This is what? Root over 500 square plus 800 square. So if you compute, how much it will come? Square root of 500 square plus 800 square and 5 over that. That will be coming out to be 5.29 into 10 raised to minus 3 milliampere, or that will be 5.3 microampere. Okay. So your they want us to find out in microampere, so 5.3 will be the right answer. Okay. So you see how you want to compute this kind of problems. So you see, I could have start from this also. Okay, it would take me 5 minutes instead of 50 minutes to explain this, but it is very important to understand these concepts. Okay, why that equivalent circuit is like that, why this equivalent circuit is like that, what should we ignore, when it will be open circuited, so that we can ignore the impedance. Okay, so ask me any question if you have at this point. Acha, is that okay?
Yes, sir, I'm clear.
So, and Tanish, is that okay?
Yes, sir.
Okay. Even if you do not understand it, just go back to the recording session, which we will be posting, and then you will be able to understand. Okay.
Okay, sir.
So, okay, let's move forward to the next question. So, by the way, Acha, you have attended the last session, right? There also this problem was discussed.
Yes, sir.
So, can you tell me that how to proceed for this problem? By the way, this kind of junction, okay, this is also N, let's say N plus, this is N, okay. This kind of junctions are known as high-low junctions, okay.
Yes, sir.
So, how to proceed for this kind of problems? See, what do we need to compute? We need to compute the built-in voltage, okay. I can write a one-line formula and you will be able to get it, but that will not serve the purpose. Anything is given, how to, what is the built-in voltage, by the way? Okay, so just let me draw this profile. This is your ND, right? This is something like this. This is 10 raised to 15. This is 10 raised to 16. Okay. This is your X and this is say 0. What is the first thing you can draw? If you know this, to all of you, what is the first thing? Can you draw the energy band diagram? Acha, you have been in the previous session, right? Can you please
Yes, sir.
assist?
Yes, sir.
Can we draw the band diagram?
Yes, sir. For P-N Junction.
No, no, this is not PN junction. This is both are N. This is N plus N junction. So suppose my device is in equilibrium now. So what is the first thing I will do to
Why
draw
is
a
it
band
empty?
diagram? Sorry.
You said N plus N. Why is it N plus N? Because they have given charge profile of P-N junction. No.
No, no. Okay, okay, okay. So just don't focus on this. Okay, this is, I told you, na, this is a high-low junction. Okay,
Okay.
let's say this is this is ND, right?
Yes, sir.
So this is a high-low junction. Both are N. Okay.
Okay, sir.
So if the device is in equilibrium, I will have a constant Fermi energy, Fermi level, not Fermi energy. My mistake. Fermi level, EF.
Yes, sir.
So from this ND, can we draw the band diagram? Not quantitatively, but qualitatively, can we draw?
Right.
Qualitatively means I do not know the exact values, but can I draw where my EC and EV will lie?
Yes, sir.
So let me just draw it here. So this is EI, this is EC, this is EV. Is that okay if I draw it like that? It is an N type, right?
Yes, sir.
So my Fermi level will be closer to EC, right?
Yes, sir.
Now tell me, this is for 10 to the power 15. So for 10 to the power 16, how will be my profile looking like? Or I would say, let me just extend this. Whether my EC will be here or here.
Above, sir.
Why above? Suppose you have a material like this, okay? This is your EC, this is your EV, this is your EI, comma EF, okay? Now suppose you are increasing the doping. Now this is an intrinsic case. Now if you are increasing, making it more N type, okay? ND you are increasing. How will your Fermi level change? In which direction Fermi level will move? If it is an intrinsic material, now I start to dope the material with N type or dopant atoms. So where will my Fermi level move now? Can anyone please unmute and tell me? Tanish? Just make an attempt, okay? It is not that you have to get it right. Just make an attempt.
Yes, sir.
So if my question is, this is a Venn diagram of an intrinsic atom, intrinsic silicon, let's say. Now if I start to dope it with donor atoms, so my device will start to become N type.
Yes, sir.
So how will my Fermi level move? It will move closer to what?
And type, sir, it will closer to valence band EV.
Valence band?
Uh, if
It is N type, right?
ach- acha, it will go to EC, closer to EC.
So this is an
Yes,
N type, right?
yes.
Now suppose I am doping it further. So how will my this move, upward or downward?
Uh,
Acha,
upward,
it will move
Right,
upward,
sir.
right?
upward.
So now see, I have given you two doping concentration. So in which case Fermi level will be closer to EC?
Yes, sir.
No, no. My question is, I have given you two doping concentration, right? In which case my Fermi level will be closer to EC? For the higher concentration or for the lower concentration?
Lower concentration.
For the lower concentration, my EF will be closer to EC.
Because for higher concentration, EC will move upwards, no sir?
EC will not move, right? EF will move.
Ah, yes sir.
Why will EC move? Why will EC move? EC will move only if you apply some potential, right?
Yes sir. Yes,
You are applying some doping. So your EF will move upwards, right?
yes sir.
See again, this your NC exponential minus EC minus EF over KT, right? So if this quantity, this distance is lesser, then this minus of this will be higher, then this will be higher. That means if your EF is moving very close to EC, you are very highly doped with N type, right? I do not know where you are not getting. Can you please ask me the question? I'll stop now. Please ask me where you are not getting.
Sir, I didn't understand because EC moves with potential. That's what I didn't get it in my head.
Again, if I dope the intrinsic semiconductor with N type, how will my Fermi level move? Will it move towards EC or away from EC? Did you
Towards.
get the question?
Yes sir.
If N type doping I am making, so my Fermi level will move in which direction? Upwards or downwards?
Upwards sir.
It will move upwards, right?
Yes sir.
More close to EC, that means more N type doping, right?
Yes sir.
Okay, if you get that, then tell me that which is correct. If you get that, then tell me whether my EC should be here or here. If this it is 10 to the power 16 and this is 10 to the power 15, both are N type.
Yes sir. So you are asking EF should be?
No, no, I am asking EF is fixed. Now in equilibrium, I am drawing it like that, EF is fixed. Now I am asking that for 10 to the power 15, I know that this is my distance, okay? So for
Yes
10 to the
sir.
power 16, whether EC should be here or EC should I draw here?
Above sir.
Why above?
Ah, EC. Wait a second sir. EF moves closer to EC with increased doping.
Exactly.
So below.
So will it not be the correct thing?
Yes sir.
Will it not be closer because it is more N type? Are you getting?
Yes sir.
Yes, sir.
Please explain why. Tanish, please explain why it is lower.
Sir, mm,
More N type doping means your Fermi level will be more closer to your EC. Okay.
yes,
Here the doping is more. So more closer means is it not more closer than this right side?
yes, sir, it's closer.
So are you agreeing with the Venn diagram what I am drawing?
Yes, sir.
So now how will the bands bend? The bands will bend like this.
Yes, sir.
Okay. If the bands bend like this, can you draw the potential profile? So what is, by the way, built-in potential? Built-in potential will be nothing but this distance divided by Q. This is Q phi bi. The net band bending is my built-in potential times charge.
Yes,
Please
sir.
go through the lectures again, okay? I think you guys are not studying properly. So if I now, this is energy band diagram, okay? If I now have to draw my phi profile, so how will it look like? My phi will be just simply opposite, right?
Yes, sir.
So if my phi is simply opposite, how will my electric field profile look like?
Differentiation of 5.
Only differentiation of phi, or will there be a side change, sign change? E is minus d phi of dx, right?
Yes, sir.
So at this point, I have a negative slope. So my electric field will be like this. It will be like this. It will go up and it will then fall. Okay.
Yes, sir.
So this is my electric field. So now tell me what is the charge? How will charge look like? Rho. What is the relation between rho and electric field?
Rho by epsilon.
Rho by epsilon is equal to what?
D phi by dx is equal to
D
d epsilon by dx is equal to.
dE by dx, right?
Yes, sir.
That which law is this?
Phi, sir.
No,
Uh, and
this is Gauss's law, right?
yes, sir.
Poisson is this. D square phi by dx square is equal to minus rho of x over epsilon, right? Just another differentiation of this. This is particular is Gauss law. So if you differentiate this, what you will get? What kind of profile you will get? You will get a zero here. You will get some charges and you will get some charges here. Okay.
Sir.
So now I could have drawn it like this and this. Why didn't I draw it like this? That I wanted you to comment on. That means this is from mathematical point of view, this is very fine. Okay, but can you tell me what is physically going on? This is some positive charge and this is, can you physically tell me what is going on when you have this kind of concentration? You have this kind of concentration. Okay, this is 10 to the power 16, this is 10 to the power 15. What is the first thing you came into your mind? Here in one place you have so many 10 to the power 16 amount of 16 concentration. Here you have somewhat less 10 to the power 15 concentration. What physical phenomena will happen?
Gun effect, is it related to gun effect?
Gun effect. What is gun effect?
It's, it's like materials में like germanium or the gallium arsenide and this is
Don't go into those stuff. If there is two different concentration, what is
Diffusion.
exactly right? You have a concentration gradient here. So there will be diffusion. Now tell me which one of you are not, which of you are not getting this is there, that there will be diffusion. Then there is serious problem.
Got it, sir.
You should have instantly tell that yes, I can see there is a concentration gradient or difference, so there will be diffusion, right? Now
Yes,
tell
sir.
me what will diffuse from left to right. What will diffuse? This is your ND, okay? That means your dopant concentration. What will diffuse?
Electrons,
Electrons. Why electrons?
because in electrons are heavily doped.
No, electrons are heavily doped. Electrons are never doped.
Answer?
In this side, your N will be equal to how much? Your ND plus, and here also N will be equal to ND plus. So if under 100% ionization condition, it will be equal to ND. It will be equal to 10 raised to 15. It will be equals to ND. It will be equal to 10 raised to 16. So electrons effectively is more on the left side than on the right side. Okay. So electrons will diffuse from left to right. And if electron diffuse from left to right, what will happen to the uh, dopant atoms from where the electrons are diffusing?
Positive charges.
So positive charges will be there, right? You see, from mathematically also we have found that positive charges will be building up at the left hand side. Is that okay to everyone? Why there will be positive charges? Because electrons are leaving their host, this your dopant atoms, okay? So dopant atoms, if dopant atom leaves an electron, it will be positively charged. So that's why at left hand side there will be positively charged dopant ions. What about the right hand side? There are electrons, right? They are moving from here to here. So it is creating a uncovered charge. But what about here? There is also dopant atoms, Nd only there. So can Nd take electrons?
No.
So how will the equilibrium be maintained? See, what happens is that the electrons which are traveling from left to right, these electrons will be confined in a very narrow region. Okay. So this is the electrons which is causing the negative charges. Okay. These are not the bound these are not the immobile ions. Okay. The negative charges at right hand side is caused by due to spillover electrons from left hand side. That's why it will be in a very narrow region. Okay. So basically if you correctly draw the electric field diagram, it will be just dropping like this. And so what happens is that all the band bending will be happening, almost everything will be happening in the highly doped side. It is counterintuitive, okay? And very low amount of band bending will be there in the right hand side or the low doped side. So these kind of behavior are seen in your high-low junctions, okay? So who was that? Parth, are you getting what is happening physically?
Yes, sir.
Okay.
Sir, one
Yeah.
question. Sir,
Yes.
why that is accumulated in very small space? Why they don't? Matlab, graph
Okay.
is why very sharp.
Right. Graph is very sharp because in right hand side, what did you have? You have electrons, right? but
Yes,
of a
sir.
lesser concentration than the left hand side.
Yes,
So
sir.
now see, there is a room full of electrons. You are entering more electrons. Will it not get repelled?
Repelled.
It will get repelled, right? So it will not be, or in other words, it will not be able to traverse in much
Penetrate.
distance, yeah, penetrate much distance into the right hand side. Okay,
Yes, sir.
so it will be almost like a sheet charge at the interface. Okay,
Yes, sir.
so this is the reason, this is the kind of behavior seen in high-low junctions. Okay, so now we want to find out the built-in potential. How will you find out the built-in potential? So to find out the built-in potential, what you can do, you can take the difference. Okay, let's say this is your EC minus EF 2, and it is your 2 just is a subscript. Okay, nothing is special about it. EC minus EF 1. So your Q 5BI is equal to nothing but your EC minus EF 2 minus EC minus EF 1. Okay, this you can easily calculate. How? You know your n, let me call this side as 2, this side as 1, then it will be consistent. Your n1 will be what? Nc exponential minus Ec minus Ef1 over kt, and your n2 will be Nc exponential minus Ec minus Ef2 over kt. So if you divide this two, n1 by n2, you will have what? NC will get cancelled. You have exponential EC2, sorry, your EC minus EF2 minus EC minus EF1 over KT. This under 100% ionization, you take the approximation ND1 over ND2 is equal to your this exponential. What is this? Q into 5BI over KT. So your 5BI is nothing but KT over Q ln ND1 over ND2. Fine. So KT over Q is nothing but your 0.026 multiplied by ln. This is 10 to the power 16 over 10 to the power 15. That means only 10. So this will be equal to your 60 millivolt. Okay. So I could have used simply this formula, right? 5B equals to KT over Q ln ND1 by ND2. This is the formula. Those of you who want to mug it up, but please don't mug it up. Okay, don't remember this formula. Please go through this step by step. This will give you better understanding. Okay, you will get to know where your concepts are getting you are getting difficulty to understand. Okay, so this is as far as high-low junction is concerned. Okay, so let's move on to the next problem. Okay, so to acha, what is this called, by the way, this device? This is your, let's say, row. Okay, let me use another color. This is your row. So this is your, let's say, minus QNA. This is
Yeah,
your
visibility is too poor, sir.
QND. Huh?
Not visible, sir.
Not
Question.
visible. If I say that this is your doping profile, some device is there which has this kind of doping profile. Okay, or if I draw the device, it will be something like this. Here you have some acceptor ions, that means it is P, and it is I, and at this place you have some intrinsic region. So what is this device called?
Pin diode.
This is called pin diode. Okay, used in power
LED.
electronics
Sorry.
to reduce the breakdown at junction. Okay, just let us understand this much. So now they have asked us that here is a charge profile of a P-N junction diode with intrinsic region given such that P-N junction is N type with this. This is your N type, this is your P type, this is your I. These are dimensions are given. So they want us to find out the built-in voltage. Okay, so how to go about this? What is the definition of built-in voltage? Just we have discussed. So I have something like this. It is rho. It is QNA, QND. Let's say here it is QNA. And this is say minus 0.5. This is minus W. This is W. This is 0.5. Okay. This is X in micrometer. So what is the first diagram we should draw? You have rho, right? So from rho, what can you get directly?
Phi.
Rho to phi. How will you get that directly?
Double differentiation.
Double, right? You have to use two steps. What if you do double differentiation of phi is rho, right? So what is a single integration of rho?
Energy,
E.
What is that?
electric
There is a
field,
name, right? Don't
electric
tell about the symbols. Call it out by names. So Acha was telling what is that?
electric field, sir.
Electric field, right? So now tell me how will the electric field look like? So your electric field is nothing but integration of rho of x dx plus some constant, okay?
Yes, sir.
Because your d over dx is rho, right? Now I just integrated it, okay? So this step like nature will be a ramp. It will follow because to maintain the discontinuity, to maintain the continuity, and it will then come down and it will be zero. Now tell me why it is constant at this place. Anyone? Why it is constant?
So that is intrinsic region.
So you are integrating zero, right? This
Yes,
is
sir.
zero, right? So if we integrate zero, it will give me some constant value, okay? Okay. So now tell me where the green color is. Okay. So this is also zero. So why this is zero?
So that is before our PN junction. That is not under consideration.
Right? Not under consideration, but yeah, but why? That is called generally neutral region, right? Where your field is assumed to be zero. But do you know the reason why?
Sir, because after some distance, uh, and this movement will be stopped to maintain equilibrium.
That
Bulk region,
is
sir.
no, yeah,
Because in
bulk
bulk
region.
region there will be
Why in
nucleus.
bulk region there will be electric field zero? That is the question.
Because the reaction is
Sir,
within only the depletion region. As it moves away from
sir,
depletion region,
immobile carrier get electric charge, so it stop the movement of the uh, carrier.
Actually, what happens is that you are all very close, but nobody is right. Okay. So what happens? Let me tell you. By the way, I appreciate the you are trying to explain it. Okay. What happens is that the amount of charge here is positive. So what is your positive charge total? Q into ND into some distance. So let me just tell what is the positive charge? Q into ND into W minus zero point 0.5. What is the negative charge here? Q into NA into W minus zero point 0.5. And your Na and ND are same. So total positive charge, let's say this is Qp and this is Qn. These are same. Do you agree?
Yes, sir.
Now, if you have a total positive charge here and a total negative charge here, and you have a bound system like this, how will the electric field line be? What will be the direction of the electric field line?
Left to right.
Right? So in this place, just where your charges are ending or charges are becoming zero, beyond that there will not be any electric field lines. Okay, so that's why your electric field will be zero. Do you get it?
Yes, sir.
That is why in PN junction also, because the total positive and negative charges are same, all the electric field lines are confined into that region only. Beyond that, we assume it to be zero. It will be, to be very honest, this we don't teach in UG courses. There will be electric field spilling at these regions also. These are related to your Debye length of the material. So that you will learn in higher order courses. Okay. So for the timing, you take it in this way that electric field will be zero. So if I draw the electric field profile, it will be zero. Then it will increase. Then to maintain continuity, it will be constant and maintain continuity, and also as your rho is zero at this place, so it will be constant, and then it will fall and then it will be zero. Okay, this much is clear. So can you tell me how will be the potential profile looking like? What is the relation between electric field and potential? For that I need to just consider a reference. Okay, I cannot consider any, that I cannot say that my phi will be zero. Okay, it depends on the boundary condition what we are applying at the end. As we are considering equilibrium, I have to consider a reference phi or voltage. Phi is nothing but your minus integration of E dx plus some constant. Fine. So what will phi look like? As it is zero electric field. Okay, just let me draw the vertical lines. So what will be phi at this place? Anyone? If I integrate 0 electric field, what I will get?
0.
0. Integration of 0 is 0. D some constant over dx is 0. That means if I integrate 0, I will get some constant, right? If you integrate 0, you will get some constant, right?
Yes, sir.
So I will have some constant, okay? So let's say this is the constant, okay? Now, how will this look like? This will look like some parabolic nature or quadratic nature because your ramp will be parabola when integrated. Do you agree? If you have x, integrate it, what will you get? You will get x square by 2 plus some constant. So this is some quadratic or parabolic nature, isn't it?
Yes, sir.
So it will have some quadratic nature. And what will be this constant integration? Constant of this integration will be some ramp. And again, this ramp, if you integrate it, you will get some parabola or some quadratic nature. And then you have a constant. Okay. So this will be your potential profile. So if I write it region by region, here it will be constant, here it will be quadratic, here it will be ramp, here it will continue the ramp, here it will be quadratic, and here it will be constant. Okay. So if I ask you to draw the electric energy band diagram, can you do it now? Yes, of course you should be able to do it. How will you do it? What is the first step? To draw an equilibrium energy band diagram?
First invert that and then differentiate.
First
Minus
step,
d5.
of energy band diagram in equilibrium.
Put negative sign. So invert the graph.
First thing is constant Fermi level. Okay. Equilibrium means constant Fermi level. Never forget that. It doesn't matter what is the system, Fermi level constant, constant Fermi level will always be true. Okay. Then this is your p type, this is your n type. Remember that. So if it is p type, your valence band would be close to this. Conduction band will be somewhere like this. Similarly, n type conduction band will be somewhere like this, and valence band will be somewhere like this. This is your EC, EF, EV. Fine. Now we just invert this plot. Okay. Why? Because any of E line is nothing but minus of Q phi plus some constant. This we have discussed. So if I let us draw this line. So it will be constant here. Then it will be quadratic. Then it will be ramp. Then it will be quadratic. Then it will be constant. Similarly, it will follow just the above plot. It will be this. It will be that. And then it will quadratic and it will follow like this. Okay. Do you agree with the band diagram?
Yes, sir.
Sure. Have any does anyone have any difficulty to understand this? How this band diagram is there? Okay. So now what we do? Let me show you some magic. Okay. Let me draw the EI also. EI will also follow. So EI will be like this. Then EI will have a straight line nature. Then it will have this and like that. Let me call this EI. Okay. Do you understand this, people?
Yes, sir.
Now tell me, where is the anomaly? You see, we have considered this region to be rho is equal to 0, right?
Yes, sir.
But you see in this region, there is some charges present. This will be what? This will be your P type. This will be your N type. Why? Because your Fermi level is like that, right?
Yes, sir.
So, is it not? Your EF is below EI in this region. Or let me say, now the pointer is there. Yeah. So in this region, your EF is below EI. That means this region of the material is P type, and this region of the material is N type because your EF is above EI. Okay. So does that mean that this is not intrinsic, right? So the way to, I'm just mentioning this, I will not explain this in this course. These are attributed to your intrinsic uh, your intrinsic Debye lengths. Okay. The actual energy band diagram of the PIN diode is much more complicated in that. There will be bumps and uh, dumbbell like nature. Okay. So this is your approximated band diagram. Okay. So anyway, but we will be able to deal with it to find out the built-in potential. Okay. Because our goal is to find out the built-in potential. What will be the built-in potential? This will be the built-in potential, right? This is Q5BI. Okay. How can you tell this? You can just simply add this distance, this EF minus EI in the N side, and add this distance, EI minus EF. It will result you the same thing in P side. Okay. So your Q5BI would be nothing but EF minus EI in the N side plus EI minus EF, EF minus EI in the N side and this in the P side. Okay. This and this, you know, how do you know that? You know that because you know your EI minus EF P would be nothing but KT ln Na over Ni. From the charge concentration, carrier concentration equation, you can compute that. Should I go into it again? I think in lecture 4 you will find that this is proved. Similarly, your EF minus EI of N, you will have KT ln Nd over Ni. So I will just have to add these two things. So my Q5BI would be nothing but KT ln this Na over Ni times Nd over Ni. Does this equation ring any bell? This is the same equation for a P-N junction diode. Okay. So if you calculate your phi bi, it would be how much? This is 0.026 into ln. This is 10 raised to 30 over 1.5 square into 10 raised to 20. Fine. So this one will come out to be 10 raised to 10 times divide 1.5 square log of that times 0.026 0.577 volt, or it will be around 0.6 volt. Okay, so your 0.6 volt will be the right answer. Okay, so let me move forward. Again, it is asked that in this question, what is the value of 2W? So what is W? 2W is this distance. Okay, 2W is this distance. How do you compute the 2W distance? The way to compute is from this diagram. Okay, let me just copy it. Okay, so do you agree that this distance is your built-in potential? All of you? If this is your Q phi bi, then it is your Q phi bi in voltage scale. So what is this Q phi bi actually? It is nothing but the area under this plot, electric field, minus W to W. Can anyone tell me how did I say that? What is your phi? Phi is equal to, just let me use another color here. What is your phi? Your phi is nothing but
Integration.
integration of, the electricity is not there. Okay, no
Ele-
issue. It will be the integration of E of x times dx, right? Now if I do the definite integration, I will need to do from minus W to plus W to find out Q phi bi, or in other sense, your phi of x is equal to integration of E of x. Okay, so phi of x2 minus phi of x1 will be nothing but your x1 to x2 E of x dx. So now if I take this point as phi of w and this point as minus w, so it will be minus w1 to w2 E of x dx. This is my minus w point, this is my w point. So this is my phi of w, this is my minus phi of minus w. So the difference is nothing but your built-in potential, right? So that is nothing but your integration of this. What does that mean? This integration means is this is minus w, this is minus 0.5, this is 0.5, this is w. So it is nothing but this integration means this area, this is your x. Do you get it?
Yes, sir.
So let me call this as Emax. Emax we know it will be how much? It will be Q times, as both the concentration are same, it will be, let's say, Na over epsilon times X depletion. What is X depletion? This is the depletion region. Q times Na over epsilon into this depletion is W minus 0.5, let's say. This much I know. So now if I want to calculate the phi bi, phi bi will be nothing but the area under this. That means your area of this triangle multiply plus area of this triangle plus area of this rectangle. So what I can do? 2 times W minus 0.5 into Emax into 1 over 2. This is the area of one triangle multiplied by 2 plus Emax into 0.5 minus of minus 0.5. That is the area of the rectangle. Fine. So what happens is that if you simplify this, it will be Emax times W minus 0.5 plus Emax. That will be Emax times W plus 0.5. What is Emax? Emax is QNA over epsilon times W minus 0.5, W plus 0.5. So I will get W square minus 0.5 square times Q into Na over epsilon. So this is my equal to my phi bi. Phi bi I have computed as 0.6 volt. So your 0.6 will be equal to W square minus 0.5 square times, what is this? This is your Q, 1.6 into 10 raised to minus 19, 10 raised to minus 10. By the way, you need to be careful that your 0.5 is in micrometer, okay? That I will need to convert it into centimeter. So if I just convert this right here only, 0.5 into 10 raised to minus 4 square, and this is 10 raised to 15 over epsilon is 11.7 into 8.854 into 10 raised to minus 14. So if you calculate your W will be coming out to be around your 0.7. This will be coming out to be your 0.78 some figure, okay? Now they are asking us to find out this 2W, okay? So your 2W would be almost your 0.78 into 2. That will be somewhat around 1.5 times something. I am not able to use the calculator right now, so it will be 1.5 micrometer around this. Okay, so your correct answer would be around this D. So if this is also you have got, then in next question you are asked to find out the electric field at x equal to 0. So this is your x equal to 0. So this entire thing doesn't change here. It becomes constant. It remains constant, and it is Emax. So Emax we know that is how much this. So your Emax you can compute out to be Q into Nd over epsilon s times x minus your, or I would say, let me just go step by step, x depletion. It will be Q into Nd over epsilon s W minus 0.5 into 10 to the power minus 4 to cater for the centimeter one. This is volt per centimeter. Entire thing will be 10 to the power minus 19, 10 raised to 15, 11.7 into 8.854, 10 raised to minus 14 into how much was W? 0.78, right? So it will be 0.28 into 10 raised to minus 4 volt per centimeter. So it will be 4.62 into 10 raised to 3 volt per centimeter. So do you have that option? Okay, yeah. So if you convert it into meter, it will be 10 raised to 5 volt per meter. Okay. So tell me if you did not understand the steps. Okay. I will explain it again. Anyone who didn't understand the steps? See, the main issue is to visualize the band diagrams. Okay. So it is very important to visualize the band diagram. So if you are given, by the way, am I audible?
Yes.
Yes, sir.
Okay. So the important fact is even if you are give any of the quantities rho, see the way to go about is if rho is given, you compute electric field, compute phi, compute energy band diagram. Okay. If your ND and NA are given, that way you can do. Another way to go about is if your ND and NA are given, you go to energy band diagram qualitatively, then go to potential, then go to electric field, then go to rho. So this is direct relation. This relation is charge balance. This relation is Gauss law. This relation is potential relation or this relation. This relation is E is equal to minus Q phi plus some constant. Okay. So this is the way to go about it. Once you have drawn the everything correctly with proper physics, then you go to the quantitative steps or try to calculate the things. Okay. For that, you need to may need to remember the carrier concentration equations. Again, those things how you can compute. You just have to integrate the density of state multiplied by Fermi level in terms of energy and from EC to infinity for n and for p vice versa. Okay. So for that, what do you need to remember? You need to GE and FE. FE, I think Fermi Dirac distribution, you are by now you will be very much familiar with it. So it will be nothing but your 1 plus exponential E minus EF by KT, and G will be there will be some constant times E minus EC. Okay. So this constant is very tricky to remember. So I would suggest you start remembering this formula, carrier concentration equation. That is your N equals to NC exponential minus EC minus EF over KT, or your P is equal to NV exponential minus EF minus EV over KT. Okay. These things you can remember, right? And suppose you are not given this, instead of given Ni, then what you will do? You put simply Ni is equal to same Nc exponential Ec minus Ei over Kt. Then you just divide N by Ni. So your Nc will get cancelled and you will get exponential. Your Ec will also get cancelled minus Ei minus Ef over Kt, right? Something like that. Okay. So then your N will become this. Okay. So these are the formulas I think you should remember and then compute your way through. Okay, so let's move on to the next problem. Okay, it is mentioned that an abrupt PN junction is uniformly doped with this, then PN junction area is this, and inductance is placed in parallel with the PN junction. Calculate the resonant frequency. So basically what they are telling me that I have a PN junction in place which I have reverse biased with with 1 volt, let's say, and I have a inductor connected, right? So how does a reverse bias PN junction act? Can anyone tell me? I have discussed this in the first problem of today.
Resistor, sir.
Reverse bias PN junction has resistor.
Wait, now sir, capacitor.
You are trying to remember, right? Think logically. In reverse bias, current will be very less. So how can there be resistance? It will be almost open circuit, right? The resistance, I have discussed this.
Yes,
Okay,
sir.
let me just go back. This I have discussed, right? In reverse bias, it will be only this will not be present, this will not be present, only the C depletion will be there, right?
Yes, sir.
So if your device is in reverse bias, you can simply, what will be the equivalent circuit of this? You have a capacitor and you have an inductor, right? What is the resonant frequency of this? 1 over 2 pi root over LC, right? This is from your circuit theory course. Now please don't tell me to explain this. I think you all know this.
Yes, sir.
So if you, so what is unknown to you? L you know. You need to find out C. What is C reverse biased? That is nothing but your C depletion, because diffusion capacitance we are not considering in this case, reverse bias case. This we have explained today, right? So C depletion is how much? Epsilon S into area over XD. Epsilon S you know, A you know, you need to find out XD. What is XD? XD is nothing but your root over 2 epsilon S VBI plus your reverse bias potential over Q into, what is the lower concentration here? ND. So it will be ND 1 over Na plus ND will be almost equal to 1 over ND, because Na is much greater than ND. So your 1 over ND will be much greater than 1 over Na. Fine. So now to compute this, what is unknown? VBI is unknown to you. What is VBI? Is nothing but your phi t ln NAND over Ni square in case of PN junction. So 0.026 ln, what is your NAND given? 10 raised to 15, 10 raised to 18 over 1.5 square into 10 raised to 20. It will be around 0.76 volt. Okay. So now if you put this in XD, your XD will come out to be 2 into 11.7 into 8.854, 10 raised to minus 14 into 1.76. This 76 plus VR is 1 volt. This over your 1.6 into 10 raised to minus 19 into 10 raised to 15. Fine. So you know now XD. Now you need to calculate your CR only. Your CR would be how much? Epsilon S into A over XD. Okay. So you compute this, then you plug it in into this formula, 2 pi root over L into C, this 1 over 2 pi L you know 2.2 into 10 raised to minus 3 Henry times you see whatever you have computed. This will be in hertz. So it will come out to be your, if you just calculate this part and plug it in here, 1.67 into 10 raised to 6 hertz. So it will be around your 1.67 megahertz. Okay. So in this way you can calculate this also. So what is the basic thing you are lacking to understand in this question is that how to treat a reverse bias junction diode, how a reverse bias junction PN junction diode acts in as a capacitor, right? As a depletion capacitor. So once you understand this step, everything is easy. And this formula, you should be knowing this. I will be very surprised if you do not know this. Okay. So let me just wrap up with two more simple problems. So it is mentioned that the current through a PN junction diode at this is this. What is the reverse saturation current? What is the formula? Can anyone tell me? ID of a diode? Anyone?
I not into e power VA by VT minus 1.
I1 V over VT minus 1. Okay. So what is the ID is given as 2 milliampere. I naught I need to find out. E to the power V. What is V? 0.1 over 0.026 minus 1. So it will be 2 milliampere. I naught. So if you compute this, it will come around your 45 point some value. So your I naught will be 2 milliampere over 45, let's say. So your, just let me do that, 2 over 45 would be your around 44 microampere, or you can say it will be around 43.7 microampere. Okay, just cross check this. You get the feeling, right? How to calculate this. This is one of the most simplest problem we have discussed today. Okay, so this you can compute. So what about this? An ideal PN junction is forward biased and moderately such that applied bias is much greater than the thermal voltage. Okay, so you know that ID is equal to your I naught exponential V over VT minus 1. Fine. So if V is much greater than VT, so e to the power V over VT is much greater than 1. So I can write my ID is equal to I naught e to the power V over Vt. Fine. So now what I will do, I will just take two cases, ID1 over ID2. So it will be I naught exponential V1 over Vt, I naught exponential V2 over Vt. So I naught will, why by the way I naught will be same for both the cases? Because it is a device, it is a particular parameter intrinsic to the device. Okay, PN junction. So what will be your this? Your ID1 over ID2 would be e to the power V1 minus V2 over Vt. So that means your V1 minus V2 would be how much? Your Vt times ln of I1 over I2 or ID1 over ID2. And we are asked that if it increased by a factor of 10, so it will be 0.026 ln 10. So you know that this will be around 60 millivolt, right? So if you increase the base, if you increase the forward bias voltage by 60 millivolt, the current will increase. How many times? The current will increase 10 times. Okay, that is the crux of this question. Okay, so I think we will stop here, and BJT I will start in the next week. Okay, is that okay?
Okay, sir.
So please go through the session again and please try to clear the concepts. Okay, please do not remember the formulas. And also, while you are making notes from the lectures, at whatever point you are not understanding anything, knowing is not understanding. Okay, you need to understand first. Wherever you are not understanding, mark a bullet point there that I do not understand this. So whenever these sessions will be there, you can ask us those questions. So in that way, instead of finding the formulas in your note, you will get to grasp the concept very clearly and it will retain for much longer time. Okay. And please, I will again emphasize that please try to clear your understanding of the band diagram very good. Okay. Because this and understanding of the band diagram will help you in solving almost all the problems in semiconductor devices. Okay. So thank you everyone. So let's end the session today here.